ME204, Curved Path Motion Using Normal Tangential Coordinates. Remember the story of David and Goliath? David slew Goliath with his sling. How does this type of a sling work? Well, David spun the sling above his head and then at the right moment let go of one end of the sling, releasing the rock, which flew in a straight line until it struck Goliath in the forehead. If we had a mass on the end of a rope and it's being swung around the center point, what would happen if the rope suddenly broke? Well, just like the stone in David's sling, once that mass was released, it would continue on in a straight line. It travels in a circle as long as there's a force holding it in a circular path. Acceleration is the rate at which velocity is changing. So let's take our mass and say that we're spinning it around a center point. It has a radius of 3 feet, and the mass is being swung around at a constant 60 RPM, or 60 revolutions per minute. How fast is the object traveling in feet per second? Well, we know that it's traveling at a constant rate of 60 RPM, or revolutions per minute, and we should be able to figure out how far it goes in one revolution by measuring the circumference of the circle. We calculate the circumference by simply using 2 times pi times the radius. So there's 2 pi r feet for every revolution. By multiplying 60 revolutions per minute by 2 pi r feet per revolution, we can cancel the revolutions and we're left with feet per minute. But typically, we want our velocities in feet per second, and in this problem, we're asking for it in feet per second. So we need to eliminate the minutes from our equation. So we have 1 minute is 60 seconds, and then our minutes cancel, and we're left with feet per second, or in this case, 18.8 feet per second. Is the speed changing? We're traveling at a constant 60 RPM, so if we're going at 60 RPM, then the speed should be the same wherever we're at on the circle. So in this case, no, the speed is not changing. It's still 18.8 feet per second anywhere on the path that it's traveling. Is the velocity changing? Yes, in this case, the velocity is changing. The magnitude hasn't changed. The magnitude is still 18.8 feet per second, but the direction has changed. If you think of this in terms of x and y coordinates, in this case, the x-coordinate, the x-velocity is 0, and the y-velocity is 18.8. But in this condition, we now have a component of the velocity that's in the x direction and a component of the velocity in the y direction. Is the object accelerating? If acceleration is a change in the velocity, then yes, we do have an acceleration. But what is this acceleration? There must have been acceleration to cause the velocity to change direction. So what is it? And how do we find it? Let's talk about a new coordinate system that we're going to use for circular motion. Well, we have a tangential direction that is always tangent to the path that the object travels on. We also have a direction that's normal to that path, or perpendicular to that path. We're going to call that the normal direction. In the tangential direction, the magnitude of the velocity doesn't change from one point to the next. It stays the same along that path. If the magnitude of the velocity stays the same, then the change in velocity with respect to time along that path is 0. So our tangential acceleration is also 0. However, in the normal direction, we calculate the acceleration by taking the square of the velocity and dividing it by the radius of curvature. In this case, our normal acceleration is 117.8 feet per second squared. Can we prove this? Yes, we can prove it. If we look at a small angle, and only in the case of a small angle can we make these assumptions, but we're going to assume that with a small angle, the acceleration is constant. So if we have a constant acceleration, we can use our constant acceleration equations. Well, let's analyze this in Cartesian coordinates with respect to an x direction and a y direction. If we look at our velocity up here, when we're at an angle of 0.5 degrees, we have velocity in the y direction, which would be equal to 18.8 times the cosine of 0.5. And we have a velocity in the x direction, which would be 18.8 times the sine of 0.5. Notice that this would also be in a negative direction. The position of the particle from the beginning point to the end point in the y direction is 3, the radius, times the sine of 0.5. And in the x direction, we're only looking at this small piece, So it's our total radius minus this portion of the triangle here. So we end up with 3 minus 3 cosine of 0.5 to get this length right here. Notice that this is a very small change in our x direction, which makes sense if we're only going a half a degree. So let's look at the x direction. Assuming that we have constant acceleration, our final velocity squared should equal our initial squared plus 2 times the acceleration times the change in position. If we solve this for the acceleration in the x direction and put in what we know, then we can calculate what the acceleration is in the x direction. Here's our final velocity. Our initial velocity is 0. This is our final x position and our initial x position. And plugging all of that in, we get a negative 117.811. And we can draw that up here with this blue arrow representing our acceleration in the x direction. In the y direction, we do the same thing, solving for a and plugging in what we know. 18.7993, this is our final velocity in the y direction. 18.8 is our initial velocity in the y direction. This is our final position and our initial position in the y direction. And solving that, we get an acceleration of negative 0.502672. And if we draw that on our figure, it points downward. But we want to know the magnitude of these accelerations to get our total acceleration. By taking the square root of the sum of the squares of our two components of acceleration, we get the magnitude of the acceleration, which is equal to 117.812 feet per second squared, which is the same as what we calculated using our velocity squared over radius equation. So this is a very important equation for us to include into our dynamics toolbox, that our normal acceleration is equal to the velocity squared divided by the radius. If you look at the resultant of those two accelerations, our normal acceleration always points towards the center of curvature. What if the rotation speed were increasing, say from 0 to 60 RPMs instead of a constant 60 RPM? In this case, now we would not only have normal acceleration, but a tangential acceleration as well, because our velocity at this point would be different than our velocity at this point up here. We calculate our tangential acceleration by using the same equations that we have used before, a change in velocity with respect to time, or dv dt. In this case, we would have an initial velocity of 0, since our initial RPM is 0, and then we would have a final velocity of 18.8, just like we had in the previous example when we get to 60 RPM. And then if we knew what the time was that occurred over, we could find that tangential acceleration. In the normal direction, we just use our equation that the velocity squared over the radius gives us our normal acceleration. Notice that the normal acceleration increases as the velocity increases. Your body feels acceleration and not velocity. This is an important concept to understand, and we're going to be using this later in the course. For example, when you're flying on an airplane, as you take off from the airport, you feel the acceleration. But once you get up to cruising altitude, you're going at a constant velocity and you no longer feel yourself being pushed back into your seat. The only acceleration that you feel is the acceleration due to gravity, which keeps you on the floor of the airplane. So let's look at another example. What if we're driving around a traffic circle in a vehicle? If you have the cruise control set and you're traveling around the circle, do you feel any acceleration? Yes, you do. Which direction is that acceleration? It's the normal acceleration that points towards the center of curvature. And we call that our centripetal or normal acceleration. If you're braking, if you're slowing down, what additional acceleration do you experience? You experience a tangential acceleration. The combination of those two would give you your total acceleration. So not only would you feel your body wanting to move forward as you slow down, but you would also feel your body wanting to move outward as you go around the circle. And the combination of these two would give you what your total acceleration is, or the resultant of your acceleration. So, some important concepts that we need to remember. First, we're dealing with a new coordinate system, a normal tangential coordinate system. The tangential component moves tangent to the path, and the normal component points towards the center of curvature and is also perpendicular to the path. The radius of curvature is important for us to calculate our normal acceleration. Velocity is always tangent to the path. There is no normal component to the velocity. Acceleration has both normal and tangential components. Here's some important relationships that we have. If we have a boat that's moving around in a circular path, we can calculate its velocity and acceleration. The velocity, as we said, is always tangent to the path, which is the same relationship that we've had before. Our tangential velocity is the change in position with respect to time, or ds dt. There is no such thing as a normal velocity. Well, we have two components of acceleration. We can have a tangential acceleration, which is our change in the magnitude of the velocity with respect to time, or we have a normal acceleration, which is our velocity squared over rho. In this case, rho is our radius of curvature. The resultant acceleration, or the magnitude of our acceleration, can be found by taking the square root of the sum of the squares of our tangential and normal accelerations. Now, it's important for us to understand what a radian is in order to move forward in this course. So what is a radian? Well, a radian is a measure of an angle. 1 radian forms an angle that provides an arc length that's equal to the radius. So this arc length, if you pulled this out and laid it flat, it would be equal to the length of this radius when we have an angle of 1 radian. What is the arc length if the angle is 2 radians? We said that 1 radian would give us an arc length equal to 1 radius, so 2 radians would give us an arc length equal to 2 radians. Likewise, what is the arc length if the angle is 3 radians? Well, if we have 3 radians, then the arc length has to be 3 of the radius. So, knowing those relationships and understanding the meaning of a radian, can we come up with an equation for the arc length? Yes. The arc length is simply the angle in radians times the radius. In this course, we're going to represent the arc length, or the position along the arc, S, as the radius times the angle in radians. So how many radians are there in half of a circle? Well, half of a circle has pi radians. Why is this an important relationship? Well, it helps us in our conversion from degrees to radians. So how do we convert from degrees to radians? Well, if we have an angle of 75 degrees, we can convert that to radians by multiplying it by pi radians per 180 degrees. In this case, our degrees cancel and we're left with radians, which would be 1.31 radians for a 75 degree angle.